Hi students, welcome to the last lesson of Chapter 9. In Lesson 9.6, we will be looking at regressions for paired data sets. And we have a warm-up for today's lesson. And in the lesson warm-up, you are asked to use your calculator to perform a linear regression on this data. So please pause the video now and using your graphing calculator and the list function, perform a linear regression and write your equation in slope-intercept form. Please pause the video now. So a linear equation that would model this data with a pretty strong fit. I mean, it's got an R value of 0.983, and remember when we look at linear functions, our most reliable predictor is the R value, whereas in the other ones we look at R squared. But both of those are a pretty strong fit, pretty positive correlation. And so an equation that would fit this data that's linear would be 32.7x minus 103.4, and that's rounded to the nearest tenth. In today's lesson, we're going to apply functions to problem situations, and we're going to use mathematical models to make predictions. So much of the data that you encounter in the real world may form a pattern, and we've seen that throughout this course. We've looked at lots of real-life applications, and we've looked at taking data and using regression equations to fit either quadratic, linear, exponential, things like that, those kind of models to the data, so that we could then use the function, the equation, to make predictions for other particular given inputs. So many times the pattern of the data can be modeled by one of the functions that we've studied, as I mentioned. So you can then use the functions to analyze trends and make predictions. So let me remind you of some of the families that we have studied in Algebra 2. We've looked at the linear function. Now the graph of a linear function is of course a line, and its parent function would be the most basic linear equation, y equals x. And in terms of the constant differences in ratios, there's a constant first difference between the y's for evenly spaced x's. So if we see a constant difference in the y's, we know that that is representative of a linear function, which would mean it would be then some sort of transformation of the parent graph y equals x, and its graph would be a line. We've also looked at the family of quadratic functions. And the graph of a quadratic function is, of course, a parabola. And the most basic function, or the parent function, is y equals x squared. That parabola that's based at the origin, that's not transformed in any way. Now, we know that a quadratic function has a constant second difference between the y's for evenly spaced x's. So if we look to see if the function was linear, we looked at the first differences and they weren't the same. Well, then we would subtract those differences, and if that was the same, that would be called a constant second difference, and that would be indicative of a quadratic function. We've also studied cubic functions. Now the graph of a cubic function looks basically like that one arm of the parabola, the parabola that would be in the second quadrant, kind of had just flipped down, and so it now looks sort of like an S shape, but it's kind of turned down the side. So you know that's what a cubic function looks like. So it sort of looks like just the one arm of a parabola just kind of flopped down. So one arm's up, one arm's down. That's a cubic function. And the most basic cubic function is x to the third power. Now, we haven't seen very many. You'd have to have a lot of data points to be able to see if something is cubic, because we know something is cubic if it has constant third differences between the y values for evenly spaced x's. So that means we would have to look at the first differences and then find the difference between those first differences. And if it's still not constant, then we'd find the third differences. So that would be the difference in the differences. And so by the time you get there, you'd have to have a lot of data points to even have any numbers to compare there at the third differences. But if they were the same, if it was constant at that third level, the third differences, that would be indicative of a cubic function. We've also studied the square root function. Now we've looked at the graph of a square root function. So the square root function is basically like one branch of the quadratic graph, the parabola, reflected over the line y equals x, because it is the inverse of an x squared or quadratic function. And so it would look something like this. Now, we haven't really looked at modeling any data with square root functions. And so this will be something kind of new. So this is how it works for the constant differences or ratios here. So there's a constant second difference between the x's for evenly spaced y's. So that's sort of the opposite of what we've been looking at. We've been looking at constant constant differences between the y's. Now we're going to be looking at differences in the x's, and the second differences in the x's would be indicative of a square root function. And finally, the exponential function. So exponential functions would include either exponential growth, which is the graph that you see here, or exponential decay, which of course would go, the other way, going like this. That would be exponential decay, but it's still an exponential function. So the most basic parent function for that is the function a times b to the x power. Now, how we know if something is exponential is that there is a constant ratio between the y values for evenly spaced x's. So this table gives us a really nice summary of many of the different families of functions that we've studied, what their most basic parent function is, what's the shape or behavior of the graph, and what is the identifying data that goes along with it. Like, how do we know if something's linear? How do we know if something's quadratic? And it usually involves comparing the y values, or looking at first, second, or third differences between the y's, or constant ratios. However, that square root function breaks the mold there. This time, that one we can tell it's square root by looking at the differences between the x's, and we're looking for the constant second differences between the x's. So let's go ahead and turn the page and look at some applications of these different parent functions. So in this example, we're given some data sets, and we might want to, write some sort of function to represent this data. Maybe this is data that was gathered from some observations or some experiment, and we would want some kind of function that goes along with it so that we could use that to make predictions for other observations. So in order to be able to use the data, we need to know what kind of data it is. So we're going to take a look at seeing if we can diagnose what type of function would best represent the data by looking at differences. So it says showing constant differences and constant ratios. So in A, we have this data set. We have evenly spaced x values. We know that they're all going up by 5. So that's the first thing we always have to check, is that we have evenly spaced x's, and we do, so check that off the list. And so then we have to look at the y values, and we have to see if they're evenly spaced. So if we look at the difference in the x's, so the difference between 23 and 98 is plus 75. And then if we look at the difference to go from 98 to 223, so if I subtract 98 from 223, I get plus 125. So I had to go up 125 to get to the next data point. And then from 223 up to 398, that's adding another 175. So the first differences are not equal. This is not linear data. So then we go to the next level. So notice when I looked at the first differences, since I only had 4 data points, I was only able to get 3 differences. When I go to the second level, the second differences, I'm really only going to get to see the change between 2 2 second differences, because I only have 3 points to look at the change between. They both happen to be plus 50. Now again, this is not a huge set of data, so I mean, if I wanted to go to the next level, I don't even have enough data to check the third differences. So it's very fortunate, I guess, that we see that the second differences are the same, and so I know that this means that this is could be represented by a quadratic function. Let's take a look at example B. Well, so I always like to check the x values and make sure they're evenly spaced. So let's see, they start off with 100 as the x, and then it went to 400, which went up 300, but then the next x value is 500 higher. So then it went up by 500. Well, this is the first time we haven't seen evenly spaced x's. And then the next pairing from 900 up to 1600 is 700. Well, that's strange. So what do we do with that? Well, typically if that had happened with any of these other functions, we wouldn't be able to really evaluate the data set because we don't have evenly spaced x values. But what this might do is might trigger the thought that, hey, what about that one, the square root function said that the second differences of the x values for evenly spaced y's. Well, we got to check to see, are the y's evenly spaced? Well, it turns out that the y's are actually evenly spaced. They are spaced by tens. And so it's like we're looking at the inverse of a linear function, because I mean, we think about the linear function, usually it's like the first differences of the y's are the same, and so, then that would be, this time the y's are the same. It almost looks like it's linear. But in fact, it's, and I meant to say, I'm sorry, the inverse of a quadratic function, because usually the second differences would be the same. But look here, that's for the y's. Now we're going to be looking at the second difference in the x's, because look here, between the second differences in the x's, it's 200. So these are changing by 200 every time. And since the y's are evenly spaced, then this is representative of a square root function. So that's what it looks like if we have a square root function. The difference, the constant difference, will actually come as a constant second differences of the x values. So this would be representative of a square root function. The reason why is we have a constant second difference of the x's. We're going to make example C a U-try question. So considering all the possible ways and different types of functions we could have, take a look at constant differences or constant ratios and see if you can determine what type of data set we have here. Linear, quadratic, cubic, square root, or exponential function. Please pause the video now. So this data set could best be represented by a cubic function because it had a constant third differences. So we had to get to the third level, the third differences, before we saw that constant value. So notice in this data set we had more points. We had 5 ordered pairs here to choose from. I'd feel a little more confident about my determination of this being cubic if I had a few more data points. But this definitely is, so far, all we've seen that is consistent here as a third differences. Let's look at one last example. Now, of course, I always want to check to make sure that the x are evenly spaced, and I can see that these are. Remember, if they're not, then that might be a trigger to think about square root function. But they are. They're evenly spaced. They're going up by 2's each time, and so I know I've got evenly spaced x values. So I might start thinking about, trying first differences, second differences, and so on. But I mean, I can already tell that I'm not going to have constant first differences. I mean, I'm already looking at a couple of these points. Like look between 0.25 and 1, and then between 1 and 4. Well, clearly those aren't going to be the same. And so I just kind of had a hunch. I thought about trying common ratios. And so sometimes, that might be the case. You might not wait till the very end to try common ratios. That's pretty easy to check. That means you just have to divide these terms in order. So if I took the y values like 0.25 and I divided it by the prior y value, 0.0625, it turns out that I get 4. Well, if I take 1 and I divide it by the prior one, 0.25, I also get 4. And of course, if I take 4 and I divide it by the prior one, I of course get 4. And so I see that there's this constant ratio, and that means I have exponential. So this is an exponential function, and the reason why is there's a constant ratio. So it's time to turn the page. So as I mentioned earlier, because the square root function is the inverse of the quadratic function, the constant differences for x and y values are switched. So quadratic, if we have a constant second difference in the y values, it's quadratic. But if we have a constant second difference in the x values, that means it must be square root. Because remember, you get an inverse of a function by just simply switching x and y. So instead of switching constant differences in the y's, if we switch it for constant differences in the x's, that means it's the inverse of the function that's indicated by the constant second differences in the y, which is the quadratic. So as a rule, when you do not have constant differences in the x's, as we saw in example B on the prior page, first check to see if the data are square root, which we turned out that in that case it was, or possibly if it could be exponential data. Secondly, if the data is neither square root or exponential, then do a regression and choose the type of regression based on the scatter plot and an educated guess. Now, also the scatter plot, what the shape of the graph, in other words, what it looks like. So in other words, if your scatter plot looks like a parabola, then it most likely is quadratic. If your scatter plot looks like a line, it could be linear. If your scatter plot looks like one of those cubic graphs, well, then it could be a cubic graph. And then another way to tell is also looking at the correlation values, the R squared value. So also we're going to and kind of make it an educated guess, but also use that R squared value. Now, when we test, we always want to test in order, so in degree order. So you'd want to start with like degree 1, which is linear, degree 2, degree 3, and so like if you got a perfect R squared value at quadratic, well then you need to stop there and use quadratic. So the first one you come to in terms of going in ascending order in degrees, that's the one that you want to choose for that particular regression equation. Let's take a look at this example. It says identifying models by using constant differences or ratio. So it said, so which model would fit the data best? So step 1, notice that the time data are evenly spaced. So we're talking about time versus height. So this is some sort of real life data that was gathered that has to do with time over years and the height. So maybe they're like measuring the height of trees or something. And so they did evenly spaced intervals. They checked every 5 years. So there's no reason to think that this is square root data because it's evenly spaced for the x values. So now we're going to go to the y values and take a look there and see if we can figure out. Well, it looks like the change in from year 5 to year 10 was 10. It went up 10. From year 10 to 15, it went up 10. From year 15 to 20, it went up 10. And from year 20 to 25, it went up 10. And that means this is linear data. Our constant first differences tell us this must be linear. Okay, the next example, we look at data, and we don't know specifically what the x and y represent here. We don't have any real life connection, but the x values are 12, 48, 108, 192, and 300. So clearly the x values are not changing on a consistent basis. The first pair of x values increased by 36, then went up by 60, then 84, and then 108. So this is, kind of looking like it's very possible that this could be a square root function. So now we want to go to that next level and check the second differences in the x's. Well, between 36 and 60, you'd have to go up 24. Well, that's exactly what I have to go up to go from 60 to 84. And then from 84 to get up to 108, you'll have to go up 24 again. And so we can see here that the constant second differences of the x's are the same. That means this must be square root data, meaning that it can be best represented by a square root function. Let's go ahead and turn the page for a U-try question. So we're going to make this example be a U-try question. That's why it says it's your turn here. This is a U-try question. So please pause the video now and see if you can figure out what kind of data is represented in the table. Pause the video now. Well, the first differences were not the same. They were 81, 108, and 144. The second differences were not the same. They were 27 and 36. And there wasn't enough data really to check the third differences to see if it's cubic. There was only just one difference. We wouldn't be able to see if it was a common difference because there's just one third difference. And so then you might have thought, well, I'm going to try common ratio because it looks like, these numbers are gradually getting bigger. Let's see if they're getting bigger by the same amount. So if you did a common ratio and you started with the first y value and divided it into the next one. So we're looking for a common ratio. We're looking to see if there's something we can multiply by each time to get the next value. And so dividing 324 by 243 and 432 by 324 and then 576 by 432. In each one of these cases, I got 1.3 repeating, so 1 1/3. And so we can see that there's a common ratio. And if there's a common ratio, this means that this data is exponential. And clearly the numbers are growing, so this is actually exponential growth data. And that's because the R value is greater than 1. It's 1.3 repeating. So if we were to enter this data and do a regression equation for this data that's modeled by exponential growth, we would get a function that we could then use to make predictions about other outputs for other specific inputs. So now it's time to look at a real life problem. It says a printing company prints advertising flyers and tracks its profits. Write a function that models the given data. So if they print 100 flyers, their profit's $10. If they print 200, their profit that they make is $70. 300 flyers, they make $175, and so on. And so first of all, we want to analyze the data to look at the differences. So I'm going to take a look at I can see that the values are evenly spaced, so I know they're all going up by 100 every time. So that means I can take a look at the differences in the y's. So the differences in the y's, they're going up by 60, and then by 105, and then by, let's see, 312 minus 175, that's 137, and then by 188, and then 720 minus 500 is 220. So it's not linear, we know that. So we can look at the next differences. So let's see, 60 to 105 is 45. 105 to 137 is 32. 137 up to 188, we would have to add 51. And then from 188 to 220, we'd have to add 32. So the second differences are not the same. Well, clearly the third differences are not going to be the same because first the data is going down, then it's going up, then it's going back down again. So we're not going to get a common third differences. It doesn't appear to have a common ratio because I know if I had to multiply to go from one term to the next, the first pairing I'd have to multiply by 7, so the common ratio would be 7. But then the next one clearly is not even, it's just over 2. So there's no common ratio either. So our next step would be maybe to make a scatter plot of the data. So to go ahead and plot the points out, and actually we can put it in our lists in our calculator, and we can create this scatter plot. Now the way that to remind you how to turn your scatter plots on and to adjust your window, I took some pictures of my calculator to show you the window, how I adjusted it. I plotted these points out, and this is what it looks like. And here's how I adjusted my window. I was using my TI-83 since I'm at home, and so I adjusted the window so that the X minimum was at 0 and the max was 1,000 because I know that my flyers printed, the highest value I see is 600. And then I did the same thing on the Y-axis because I can see that the profits, the highest I see is 720. So that should clear them all. I also changed the scaling on both to 100, so each tick mark represents 100. In the case of the X's, it's 100 flyers, and in the case of the Y, it's $100. So then that way, if when I do graph the scatter plot, I can actually see them on my window. But how do I actually get the scatter plots to come on? Well, that means you have to turn on your scatter plots. And a quick reminder on how you do that. It's under the y equals menu. If you hit the second and the y equals, and you just come down to number 5 and you turn your scatter plots on. And you got to make sure to go back and turn those off later on. But when you do and you hit graph, then you get this scatter plot. So this scatter plot looks to me like it's either exponential growth, which clearly it wasn't because we saw that there's no constant ratio. Now, the second differences were close. I mean, they weren't too far off. And sometimes data is not perfectly fit. Sometimes we won't get an r squared value that's exactly 1. So maybe we could try quadratic. So that's what I did. I thought, well, it looked enough like some sort of parabola, at least one branch of the parabola, that I went to my calculator and I checked quadratic regression. And I found out that the r squared value was really, really close to 1. So it actually turned out to be a pretty good fit for the data. And so when I graphed it, I put that in my y equals. You can see that the line just goes right through those data points. You can see it just pretty much picks up every one of those plots right there on the graph. And so I'm going to go ahead and use this regression equation to describe this data. So I'm going to say f of x, where x represents the number of flyers printed, is equal to 0.002 x squared plus 0.007x minus 11.2. So the process was to take a look at the data and analyze it in different ways. Analyze it by looking at common ratios, common differences, examining the scatter plot, in other words, the pattern of the points when we plot them. And then using the tools of our calculator to calculate the correlation using the r squared value. All of those taken into account will help you make the best decision on what function best represents your data. So that does it for this lesson, and I'll see you in class.